Yes, two-stage op amp and some knowledge on PLL.
So what you have done in
PLL,
two-stage op-amp?
we have designed a two-stage op amp amplifier with phase margin of 60 degrees, and also to
Okay,
achieve a unity gain bandwidth of around 100 megahertz. Also, slew rate. There were some specifications given. Slew rate
okay,
should be like 20 watt per microsecond and all. We try to bring the specifications.
okay. So which architecture you opted? Like, can you tell a little more about that?
Can I draw the spectrum
Yes,
also?
yes, you can draw. Yes, you can draw. You can take the pen from here and
Yes. I'm not drawing the bias circuit. So this is some bias current. It
okay,
will be given from
okay,
current measure. So
okay.
this is my first stage. Now says second stage.
So you used Miller compensation.
Yes. And also here we have given a like this common drain for reducing, making the output impedance as zero. This is a simple common drain amplifier.
So what you were driving here? What a load?
We didn't keep any load here. It's just a capacitor of 1
No,
picofarad.
no. Why you use this common drain then?
Just to make the output resistance as zero, sir, because if we use only these two, just the two stages means like output
Mhm.
resistance will be higher. Just for the idea, we implemented a common drain.
So you were not driving any load, just you put the common drain here to minimize the output impedance.
Yes. The project, the idea is to design only till here, sir. This one we just tried. Like as an ideal op-amp parameters we studied earlier. Output impedance should be zero and all. Just to understand that thing we
So
have tried. And
okay, so what was your expected UGV for this structure?
our expected UGB is 100 megahertz.
100 megahertz. So what was your the Miller cap?
My Miller cap is around, um, I don't remember the exact value, but it is around 2.3 pico to 4 pico. So I guess.
So you might have the knowledge of like first stage GM,
Yeah.
what it was.
Since the unity gain bandwidth is very higher now, here 100 megahertz now, the W by L
Mhm.
values and GM values, generally we say that GM, when the unity gain bandwidth is around 1 to 10 megahertz, we can expect a GM in micro Simon range. But since our unity gain bandwidth is higher, we got a GM in millisiemens. For these both, say this transistor is 1, 2, and 3, and 4. For 1 and 2, I got my GM in the order of millisiemens. This is around 2 or 3, like that. Something like that.
What about the GMs of 3 and 4?
GM of 3 and 4, I don't remember the exact values, but in
No,
the
no. What was the range
around,
like? Why you kept them high or low, whatever?
yeah, this high or low is depends on the unity gain bandwidth. So since the unity gain bandwidth is higher, while we calculated this.
Does the GM of transistor 3 or the transistor 4 comes into picture in UGB?
No, this doesn't come under the UGB, but it depends on this load current and all like that. No?
GM of
This
3 and
current
4.
will, yeah, GM of 3 and 4, like GM of 1 and 2 are directly dependent on this unity gain bandwidth. No? But
So
3 and
what
4 are
about the
not.
GM of 3 and 4?
GM of 3 and 4, um, we got it, but like one more assumption what we made was like this thing. So we assumed a minimum common mode range and maximum common mode range inputs for these things. And we have made a like we found one overdrive value for proper operation of the 3 and 4 MOSFETs, and we got GM3 inputs.
Okay. So like mm, and like have you ever think that what is the importance of GM of 3 and 4, or just it is set by your like current and whatever overdrive you means designed for, or is there any importance for GM 3 and 4 in the picture?
Hmm. Like from the knowledge I got from the circuit, GM of 3 and 4 and this GM are dependent, sir, again. Like in this circuit, this capacitor plays a very important role. No? Like
So
according to
if
this
I keep yeah
capacitor, we can
if I keep GM of 3 4 high, then what is the problem?
GM of 3 and 4 as very high.
Means yes, whatever you kept it present, if I'm keeping it higher than that, like a 10 times of that what we have used presently, then what can be expected problems in your circuit?
As we increase this GM, sir, this GM will be also so much increased actually.
Why this GM is dependent on these GMs?
Because like in the derivation, there will be few equations, you know, so like uh, this
So how much
capacitance
power you
value
burned in the
and
first stage?
um, in each stage we didn't calculate. So in the whole thing, it is in milliwatts. So
Oh, how much milliwatt? Like
around 4.3. I don't remember the exact number, but it is around that.
milliwatts.
Yeah.
So like which stage current is more important? The first stage you want to burn more current, or second stage you want to burn more current? What do you think, and why?
Second, yeah, second state. I guess second state should um, burn more current.
Why?
Like this has to compensate the this extra poles which are coming and all. Maybe
Where it is coming
this
extra
first
pole?
stage because like in the first stage we'll have two poles now, sir. Like we can expect one capacitor here. Say this is C1 and one capacitance here C2.
Okay.
And assuming all the remaining poles are so far of the unity gain bandwidth, we can take two poles ideally. So
So
if
you
I
expect two
simply
poles
in the
only, or anything else also from first stage?
yeah, there will be a zero also, sir. There will be a zero.
Where?
Like location of the zeros.
Where? Yes.
I can there. I don't remember the exact formula, but I know the idea of deriving the zero. Sir. Can
How
I
will you
just
calculate zero in the
derive?
first stage?
Yeah. So can I get some white space? Can I go down?
Yes.
These are ground. I am assuming an equivalent capacitance C1 here. If we are doing it in the differential mode now, so we can ground these things. Um, so I am assuming my V1 as some common mode voltage plus differential mode voltage by 2, and my
Okay.
V2 as again some common mode voltage minus differential mode
Okay.
voltage
Fine.
by 2.
Fine.
So
Okay.
my V1 will be now VD by 2. My this V2 will be minus VD by 2. And
Hmm.
so now the current which is flowing in this MOSFET is, say I am assuming ideal GM for these both transistors. So I1
Say,
is equal to, sir?
Hello,
Okay, okay, you can continue.
hello,
Yeah,
Chandrasekhar.
yeah, yes, yes,
I have one doubt. You said here you will take ground for a differential signal, right?
yeah, yeah, yes,
Yeah, can you justify that one? Why you taken the ground
yeah,
when we are analyzing
yeah,
the differential
yeah,
signal?
yeah, yeah, sure. For that, I am taking one basic two-stage, I mean, single-stage on amplifier, sir,
Hmm.
not this thing. So I am just since we are doing an OC analysis, our
Hmm.
I mean, this is just a biasing only, na, sir. So we can assume it as a open circuit.
Okay.
So let this voltage be some Vs, sir.
Hmm.
Okay, this is some VD by 2, and this is some minus VD by 2, as mentioned before.
Okay.
Now, due to this voltage, GM
Hmm.
VGS current will flow in this direction, and the GM VGS current will flow in this direction for this and this.
Okay.
So applying KCL at this node, uh, we can,
Okay.
as mentioned, like if we consider ideal GMs for both the transistor,
Hmm.
VGS1 is equal to VGS2. Na? So
Okay.
VD by 2 minus Vs is equal to uh, minus VD by 2 uh, minus Vs.
Okay. Got it. Okay. Fine. So
Yeah, right.
here the differential signals you are
Uh,
saying one is VD by 2 and another one is minus VD by 2. So can
minus,
I take
yes.
uh, one is VD by 3, another one is minus VD by 2? Maybe. Is that possible? Anyhow, I'm
Again, that,
giving signals differently, right? Differently. It
yeah,
is not a single
yes.
signal.
So I feel that it actually depends on our constraints. Like it is our wish. Suppose I want to use, if I assume like my input is 1 volt plus 1 millivolt sine omega t, na, suppose.
Hmm.
Our idea is to amplify this 1 millivolt only. Na?
No, no, no. That is
So
okay.
effectively what our output,
Amplification and all, I don't care about that one. I may use some different circuitry as well. What I
yeah,
am
yeah,
asking was, is there any
yeah.
possibility in any circuit? I will have one.
Hmm.
I will have differential
Uh,
voltages as VD by 3 and minus VD by 2. Just I am asking whether it is possible or
no,
not,
no, no, sir.
and
VD
why,
by 3 and sir,
and why.
suppose if we are, yeah, suppose sir, if we are targeting to for V volt, sir, suppose say VD volt,
Hmm.
our effective input should be, then
Hmm.
we should split the signals accordingly only, sir. Otherwise, because our output expression is V out by our gain expression, output by V1 minus V2, it will be there. No?
Okay.
So,
Okay. Then I
however,
will.
you assume these signals, the effective signal should be your V input, like as mentioned in the question itself, sir. And since here I am assuming an equivalent with a different 180-degree phase, still it will be like VD only. Na? Suppose
Why
if you
180
as
degree? Why 180 degree phase? I don't say I don't want any 180 degree phase. Let's say I am giving two sources. I have two sources. So I am giving separately. So still that might be possible or not. You are saying 180 degree phase, but why that 180 degree phase every time you are constraining
yeah,
in that particular point
yeah,
itself?
yes, sir. So
So
this
I
one,
have one source.
suppose if
Let's
the
say
delay,
I have one source. It is having some V plus some VD by some whatever the voltage, and I have another source V plus some two VD, some whatever signal I have. So we are playing the signal with these two signals actually. When we are talking about the differential, we need to care of two signals, not single signal. So I have two sources. I
yes, sir.
need to analyze the differential and common for these two itself. So that's why you are using differential MOSFET, like differential amplifier. You are saying.
Yes, yes,
So you are
yes,
saying about the 180-degree phase, everything you were saying, but that I who no one cares about the 180-degree, right? Maybe or may not be. I don't know because because I am sending only DC. I will send only DC. We
okay.
can we can do AC analysis. We can do analysis for DC signal as well. Even though DC is having some common signal and some no, what can I say? Some differential signal with small ripple. You said,
And
yeah,
some
AC.
noise,
Some noise
yeah,
will be there.
some,
So how can you sure
Hmm.
that every time the noise will come at exactly 180 degree? How can you sure? We are saying 180 is okay. If
Hmm.
you are saying 180 degree, okay, one will come positive, one will come negative. But how can you, how it is every time it is possible to get 180 degree if you have two signal? No,
Like in real world signals, we cannot sure. Yes. This is for
but they
analysis,
are,
we generally consider may or may not.
yeah, that's correct, correct. The real signal we cannot justify, but analysis perspective we can do. But why? How do we
Uh,
correlate? Like normally, first basic definition is there. Instead of going into
yeah.
math, there is some basic definition for common mode signal and differential signal is there. So I want in
Okay.
that perspective, definition perspective, not like any maths or any solving. I think you came little bit. Think about that one. You were still telling in terms
Yes,
of
sir.
180 degree, I need to give minus symbol. But what I asked was why it is not possible or why it is possible. I have different differential signal because I am giving say, separately sources. That's why I'm asking.
Mm. So for you are asking for two different complete sources for this cheating.
Yeah, whatever if you want, you can take common, different. See, our statement need to valid for all the universal cases. I am not fixing that is it common source or different source, nothing. Actually, the statement is valid for all the things, irrespective of phase also. I am not even caring about phase. Everything, everywhere it will work, the statement. Okay, it's fine, or you can think about that one. So we'll talk that one later. It's a basic
Okay.
definition only.
A-
Yeah,
As
Anuj, you
of now,
can
you
I
continue.
can
have one
continue,
small
right?
answer.
Okay.
I have one small answer for that, sir.
Okay.
Maybe I have one small thought about that. Sir, if I assume I give two independent voltage sources, say V1 and V2, sir, in
Hmm.
real life, we don't know, as you mentioned, whether it may be DC or it may have some AC ripple also. You know.
Yes.
I can assume for my calculations, sir, if I am the designer and I am designing this circuit, no, I can take VCR, I mean, one common mode voltage and one differential mode voltage. No?
Yeah,
So
that
I
is
can take my
true.
common mode, yeah, I
Hmm.
can take my common mode voltage as their average, not always identical, na, as we
Okay.
can change that.
Hmm.
And we can take the for differential mode thing, we can give V1 minus V2, something like that. It will be same anyways.
Yeah, that is the exact answer. That is the exact answer I want. You are
Uh,
not saying this one from
yeah,
start. Every two signal
yeah.
can be represented. Yeah, the term is important.
As yeah,
Representation.
yeah,
We can
yeah, yes.
represent any signal in terms of common mode and
Yeah.
differential.
Common
That is
mode,
what you said. That
differential
is
mode,
correct.
yes.
V1 plus V2 by 2. Ultimately, this is playing with numbers only. V1 plus V2 by 2. We are
Yes, sir.
assuming. For ease
Well,
of analysis, I can take
yes.
any point as ground. Ultimately, the potential and
Mm.
energy will remain same in the circuit, right? So our ease of analysis,
Yes,
we
yes.
will take as common mode and differential mode. The common mode will be V1 plus V2 by 2. This is exact answer. It is the correct one. If we take DC, we will get
Yes.
the same thing. If we take AC or mix, whatever you take, this statement will give proper answer. So this one I want. You are
Yes.
saying 180 degree, 180. It will not perfect for
Yeah,
every case. So this one I
yeah,
want.
yeah, every case.
Correct. This
Yeah,
is
yeah,
this
sure.
representation is there, right? The two any two signal we can represent in terms of common mode and differential mode. This is a good statement. This one I want. Now it is correct.
Mhm.
Yeah,
Yeah,
you said correct. Fine.
okay.
Yeah, Anuj, you can continue.
I continue. Yeah.
Okay.
Sir,
So we were
also,
there as
I'm assuming
a zero location, pole location, and
zero.
what's the other
Yeah,
pole is there?
yeah, sure.
Hmm.
I'm assuming my equivalent capacitance at this node as some V1 and here I am assuming some C2.
Okay.
Sir, due to this, sir, in this case, I'm considering equal, I mean, equal signals, sir, VD by 2 and minus VD by 2.
Hmm. Hmm.
Is it fine? So, say this current I1, sir. I1 equal to GM into VD by 2.
Okay.
And this current will again split in this one and this one again. So,
Hmm.
say this is some I3, this is I4, this is I2. And this is the resultant current which we want. I4 minus I2.
Hmm.
So, sir, we need to find the current in I2. Now it is like some voltage divider here. I mean, sorry, current
Okay.
divider here. So this current
So
will be,
yes, I got the
yeah,
idea.
so
Like you got two paths, and finally the current what you are getting
yeah,
at the output, you will equate
current
it to zero.
mirroring. Uh,
Yes, yes. Anyway, we got two
we'll mirror
paths,
the
and
current. Yeah, yeah. So from this again, I can use this say I4 minus I2 as some effective I out, and I
so
is
what the
equal to
roughly
some
number
current.
comes for the zero?
Um, maybe
Zero comes 2 GM 34 by C, whatever you assumed C1.
okay. Sir. Yeah, yeah, yeah. I forgot
Yes,
this.
no? And what is the pole
Yeah.
there?
Here, sir.
Yeah, yeah, there is a pole also, no? And Miller pole that you
Yeah,
initially
one.
told that there are two
Uh,
poles.
yeah, yeah. This pole will be 1 by GM2 into this is R0 3 parallel R0 4.
Hmm.
This is one pole, sir.
Uh,
And the other is
no,
um,
yeah, this pole, mirror pole I'm talking about, mirror pole.
okay, mirror pole. This 1 by C1 into approximately it is 1 by GM3.
You can say it is GM3, 4 by
GM3,
C1.
4 by C1. Yes.
So FG due to mirror is 2 times due to F4 due to mirror. Roughly this number comes. So what is the
Yeah.
first is main pole comes at?
First is male. This is the dominant pole, sir.
Which one is dominant pole?
This one.
How you are saying dominant pole? Is there any without
Like this
splitting in the
R
mirror, without using the
uh,
mirror, what is the order of poles from the first and second stage?
without splitting this thing.
Without splitting.
Yeah.
Now you are not, as of now, you are not using any splitting term there in the pole calculation on top.
Yeah, yeah, yeah. Sure. I can reduce my this diagram like this, sir, simply.
Hmm.
So this
Yes,
say
yes,
my
GMs. Wait,
effective
wait, wait, I am giving you more space here. So you simply want to like create two GM
simplify.
sets.
Yeah,
Maybe you
yeah.
simply want to create
Two
two GM
normal
sets,
amplifiers. Uh,
GM1, GM2. And here you told that this is
but,
your first parasitic pole. This
but
you
I'm
told that
not.
your
Sir, excuse me. The space is not visible for me.
not visual to you.
No, sir.
In this
My
here,
old
one
screen place.
purple color option is there, right? In you can click on that follow Anuj Chauhan,
Click
one
on.
option will be there.
Oh,
Yeah, just click on that one. Anuj Chauhan is presenting follow. That white color notification pop will be there, right?
okay, yeah, yeah.
Yeah, just follow that button. So you will be able to track
Right.
the Anuj Chauhan window.
Okay, sir.
Okay. So as of now, we are not concerned about whatever the mirror and zero inside the first stage. We are simply
Okay.
interested in here we are applying some input and other side we can consider it. And here you are applying some like
Horizon.
CC. So now you roughly tell me what are the poles and zeros here.
In this diagram.
Yes, it's complete structure. And why are you using like the Miller cap and Miller this
Yeah,
RG here?
yeah, sure, sure. Sir, I'm assuming output capacitance, output resistance as first stage of for second stage it is R2. Okay.
Oh,
Without
yeah,
this
that
compensation,
also, yeah, that also it can we can consider here. You want to say R not one for first,
one
and here
uh,
R not two for the second.
R naught. Yeah. So my without any compensation, my first pole will be uh, 1 by R1 C1, and my second pole will be 1 by R2 C2, sir.
So C2, okay. So we are using CL, means load here. Anyway, if load is not here, you will use C2 here. Okay, fine.
C2,
If
yeah.
load,
So I just
yeah,
simply told.
if load is not here, we are doing C parasitic 2.
So, so after using this Miller compensation, So this capacitance will. So I am assuming first there is no resistor. So since Miller capacitor, I mean Miller technique, we mainly do here for capacitor. Resistor comes again at the last node. It's for right hand zero, which comes. So I'm assuming I don't know there is a zero here. Only capacitance. Here my capacitance
Hmm.
will be will be C1 into 1 plus. Suppose I am assuming my gain as A. This will be 1. Anyhow, amplifier's gain is negative, na? So 1 minus of minus A is I'm writing as 1 plus A. And here it has, uh, sorry, this is CC.
What about second pole? Can you write it quickly? First pole I got.
CC
You split
into,
it the mirror.
uh,
You split it the mirror cap, and just it is a number that is R1 and this cap. What is coming at the first node?
yes, sir. Now the capacitance here is increased, na? This pole
Hmm.
will move a
Yeah,
bit
that is
like
fine.
here,
That is fine. So it can
and
be
this
considered as
pole will
dominant
go,
pole now.
yeah, this will be the new dominant pole.
So what is the second pole exactly? Where you're expecting second pole?
The pole corresponding to this one, sir.
Yes, yes. Where it is coming?
Yeah, this is like, say,
Include
suppose
CL
assume
also.
this CL also. Okay.
Yes.
So, um, so this will be CL parallel to this. I call, suppose this is CA, 1 by CL parallel to CA into uh, R naught. This is the location of the second impulse.
Is it correct? Do you think R02 is correct here? Impedance looking from outside is R02.
Yeah, without any RZ, is R naught 2 still.
No, no, without RZ also is it R02? Do you think?
Sir, can I draw a diagram for my simplicity purpose again? Visual.
Right. Yes, you can draw
Some
down
lights.
here. Yeah, you can draw down here.
Um, So, as you have mentioned, I'm drawing a small signal diagram. This is my R1. This is my C1. This is the capacitor which I have introduced now, Miller capacitor. And again, this dependent thing and the R naught, I mean R naught 2. And this is C2. This will be my V input. So, I can apply node analysis at this thing. V1 minus. I think I should solve this circuit for saying the second pole.
Oh.
This is the equivalent circuit diagram after the introduction of this Miller compensation.
So what roughly number comes at? Any idea? Actually, from the second stage, first stage pole you got, the dominant pole we got is fine.
The
Let's say if
dominant pole, yeah, yeah,
dominant pole was this that we were getting. Two means R not one.
or not one.
Then
So
gain of second stage, and then C. So the expected first pole. But second expected pole comes GM2 by CL. You have to think about it. How this equivalent impedance from
yeah,
outside is coming is 1 upon GM2.
yeah, yeah.
Here is a
Okay,
no
okay,
term of
sure, sure.
R02. There is a no term of R02. It simply
Okay,
means
sir.
if you have GM2 stage, then when you are looking from outside, this R out is coming as 1 upon GM2. Why
One
it is
by,
coming so why it is coming so you have to see it.
yeah,
R02 is here, but here is a like this is let's say 0. And I mean to say, here is a capacitive division. This is parasitic 1.
Yeah. Yeah.
This is CC roughly.
Mhm.
So when we used to see like this pole or this impedance when we calculate from the outside, now we test and I test at higher. This pole generally comes at higher frequency because we are splitting it and we are
Yeah.
assuming it's coming at higher
Yeah. Yeah.
frequency. So
That's
what
it.
you can say at higher frequency there is a capacitive division, and according to
Mm.
capacitive division here the voltage comes is like roughly when we are
CC
calculating.
by maybe
So
CC
this
by
so
CC.
yeah, so about R naught you will see that whatever voltage applying here roughly it will come here, you will see this is 1 upon GM2. But when we calculate like capacitance from here, what you will see there is CL also. This CL, CC and CP. The CL is parallel with series of CC and CP, which is CC,
CC plus CP.
CP1, CC plus CP1. What we see, Miller cap, let's say CC is much greater than CP1 because it is a parasitic. So
Uh-huh.
we can
Yeah.
assume the output capacitance looking from the outside is like it is
CC.
CC is greater than so CP1. So CP again is
Ah,
small,
yeah.
so roughly it comes as CL.
CP
That's
only.
why it is CL
Okay.
only and impedance that we are a 1 upon GM2. You need to
Okay.
verify
Okay.
it. This is the second
Yeah.
pole.
That's right. Mm.
Okay. So what is the UGB of the system?
It is GM2 by
UGB
CC.
expression. GM2 by CC.
GM1 comma 2. GM1 comma 2 by CC.
Okay, means GM of first stage you want to say.
Yeah. GM of
G-
first stage. I mean, 1 and 2 transistors I mentioned above
Okay,
in
got
first
it.
stage.
So this is your FUGB
2
2
by
pi.
1 by 2.
Okay, so where your pole second pole is coming as GM of second
By
stage
CL.
by 2 pi CL.
Yeah.
Where first pole comes as 1 upon
1 by
R naught 1
GMR not.
A2 CC
Yeah. 2.
2 pi
Mm.
CC. So when it comes to these two poles, we ideally want what? This pole 2 should be higher than the UGB so
Higher
that
than
we
the
have good
USB.
phase margin. So we have a
Yes.
good phase margin. So from the here we can like compare GM2 or GM of second stage, whatever in the relation with GM of first stage. It is 1 2.
Yes.
So accordingly, when we burn more current in second stage and when we have more GM2 or from the GM second stage, then what we can have our second pole outside of the UGB, which is good for the phase margin.
Okay.
But for better UGB, we also want like a first stage GM should be more. So
Mm.
it depends on what application you are using for. If you want like a
Application.
more GM from first stage, if you want more GM from first stage, then we have to run more current in the first stage, or we have to size the transistors in the first stage strongly, or sometime in the strong, or, apart from a strong inversion, sometimes we also size them in sub-threshold region, so that we can have more GM for particular current, which is better in terms of getting good UGB. And
Mm.
also, if you ever think about the mismatch and noise contribution from this first and second stage, this thing also
Yeah.
decide what
Yes. Yes, sir. We didn't
this thing
look
also
much into it.
decides. Yeah, okay, okay, no problem.
Yeah.
So this thing also decides. So when you're like talking about noise and offset or mismatch,
Mm.
then you will see if you keep GM of first and second stage high and GM 3 and 4, which is Miller, it's low, then it is good for noise and mismatch.
Okay, sir.
This exactly expression comes that you can see this thing. But as of now, roughly I am telling, if you want to see the input referred noise or input referred offset, then the expression generally comes inversely proportional to GM of like 1 and 2 square, and it comes directly proportional to GM of 3 and 4. That's why I told the GM of our current mirror we used to keep low because we have to reduce the what mismatch and means noise and offset, and we keep GM of input pair, which is 1 and 2, more so that again it can be reduced, mismatch and noise.
Yeah.
There is a complete expression you can also derive, but as of now, I'm just telling the relation. It is directly
Yeah,
and
I will
inversely
check.
proportional. Okay.
Yeah.
So this was about your project. Okay, fine. What are the supply for your project? Means two-stage open?
1.8, 1.24.
1.8. Okay. Common mode was 0.9.
Common.
Do you know the
Minimum
technology
was
of
we assume
MOSFET? Which technology are you using? Are you designing?
for this design we have used the GPDK 180.
I mean, that is related to which nanometer?
180 nanometers.
180 nanometer.
Uh-huh.
Which simulation tool you use?
Cadence and design.
Cadence.
Okay, so this session is going to end within 1 minute. So
Yeah.
I think I'll launch a new session in within 10 minutes because it
Yeah.
will require 10-minute time.
Okay.
Okay.
Okay.